In this video, I want to talk about one of the most common methods used in machine learning, data science, econometrics, and so forth. Across the board, probably by far the most common method used for estimating relationships between variables is the linear regression model. So here you see an example. If you think of a scatter plot, where we look at the relationship between two scale level variables, so two variables where we can have values along a scale on all kinds of places, then we can often think of a linear relationship between the two. If you would see a flat line here, it would suggest there's no relationship between the variable on the x-axis and the variable on the y-axis. And if you see an upward slope, there's a positive relationship. If there's a downward slope, there's a negative relationship. And sometimes relationships are not so linear, but the linear regression still captures the main trend that's in the data. There are of course cases where it really misses the main trend. For example, if it has a parabolic shape, it goes down and then up again. A linear regression will not capture that. But in many kind of cases, a linear regression will capture sort of the average main effect. So here's an example of people responding in a survey that immigrants contribute to the Irish economy, and whether they favor EU integration or not. And those who think that immigrants have a positive effect on the economy are much more likely to support European integration than people who do not think immigrants have a positive impact on the economy. So we can see that there is a relationship between those two. And linear regression is about estimating this model. In the social sciences, we are usually after some kind of explanation. We want to understand why some people support EU integration and others don't. And so we look at this as one possible explanation. In machine learning or data science, we are more after predicting. We're trying to predict whether somebody will support EU integration or not. But in both cases, the linear regression is a very helpful tool. We can formulate the linear regression in an equation. The equation always has the dependent variable on the left, the y variable, then a first beta coefficient that shows you the intercept. This is the value of the dependent variable when the independent variable is 0. A crude way of formulating would be to say where the line crosses the y-axis, but this is only true if you draw the y-axis where x is 0, and that's not always the case. And then we see beta 2 in this case here, that is the slope coefficient. It tells you how steep the line is. If it is 0, we have a horizontal flat line. If it is positive, we have an upward slope. If it is negative, we have a downward slope. So beta 2 in this equation really shows the relationship between the independent variable x and the dependent variable y. So if we go back to the previous slide, y would be support for EU integration, x would be thinking that immigrants have a positive impact on the economy. And we also know that all the points in the data are of course not exactly on this line. This line will show us the average trend in the data. It does not show us where all the points are. And to mathematically capture the deviation between those points and the line, we have this error term or residual. So sometimes we use an e, sometimes an epsilon. I'll clarify in a few slides what the difference is exactly, but it denotes this difference between the line and the individual point, between y and between where we will predict y to be given this regression. An important feature of the linear regression is the level of parsimony. Parsimony means that it's a relatively simple model. Here we estimate only two parameters, beta 1 and beta 2, and this describes the entire relationship between x and y. The advantage of parsimony is that it's simple to interpret, but also it's usually more easy to generalize. So we can find this relationship in this data set, but we can also hope that when we collect more data, we find a similar relationship. If we use this linear regression to predict what y will be given x in some new data set, we could put a bit more trust in that it would work. If we have very complex models that capture all the intricacies in the relationship between x and y in a particular data set, there's a very high risk of overfitting, that the model will work well in this particular data set and do a much more precise prediction than a linear regression. But once we add more data, once we add a new data set, that model might have been too fine-tuned to the data set we first had and actually perform worse in the new data set. So the simplicity of the linear regression has major advantages, because it means that we get a more crude version of the relationship between x and y in this dataset, but it's more likely to still be a good summary of this same crude relationship in later datasets. Whereas if we have a much more complicated, refined model, we run a high risk of overfitting, of fitting a model very precisely on this particular dataset, but telling us much less in general about how these x and y are related. I told you I will get back a little bit on this difference between errors and residuals. In the original model, we talk about x, beta, y, and epsilon, where epsilon refers to the error term. And the error term says that in the wider population, or in nature, we expect there to be a relationship between x and y, and we can capture those with a linear regression, but we also assume that there is much more variation in y that is not captured by this linear relationship, and that is captured by the error term, epsilon. Once we have a particular data set, we have a sample and we have data in those, and we have specific observations, we can run a regression and we estimate these beta values. And I will use het for estimated values. So beta het is our estimate of the actual relationship in the population beta. Once we have beta het, we can multiply x by beta het 2 and add beta het 1, and we will get a prediction for the dependent variable, and we can call that y hat because it's a prediction. And there will be for each observation a difference between this observed y and our predicted y hat in this particular dataset, and that difference we call the residual, or E. So E is the residual of a observation, which is the difference between our predicted value for that observation and our observed value for that observation. Whereas epsilon captures in nature the variation in y that is simply not captured by this linear relationship. But we're not talking about a specific observation in our data. So the residuals are the vertical distances between each point in the data and the line. Now, just to confuse you, this slide shows you what I mean by vertical distances, but unfortunately it is called error term here, this should be residual. So the residual is the distance between each point and the line. And the regression line is this blue line here. And these distances are always vertical, not perpendicular to the line. So it is helpful here to get the terminology straight. Y we in political science tend to call the dependent variable. It is also called the regressant or sometimes the outcome variable. X is the independent variable, the variable that does the explaining. So it can also be called the explanatory variable or the regressor or the predictor or sometimes even factors or carriers, but these are less common. But predictor, regressor, explanatory variable and independent variable, they are all very commonly used. They all refer to these X variables. We can say that Y is regressed on X. And an important distinction is the difference between the population parameter, the beta, the value that we in nature, in the world, think is captures the relationship between X and Y, and beta het, which is the estimated coefficient, which tries to capture the parameter. So we estimate the coefficient, we call this beta het, and our aim is to get as accurate an estimate as possible of the population parameter. And then there's the error term or disturbance, which is the difference between y and the predicted linear relationship between x and beta, beta being the population parameter that we cannot observe. So in nature, it is a difference between y and the linear predictor of x and beta. Whereas in a particular data set, we have residuals, which is the difference between x times our estimated betas, which leads to a predicted value of y, and the difference between those is the residual. So to estimate a linear regression, we need to come up with estimates of beta 1 and beta 2. And for that we normally use ordinary least squares. Ordinary least squares minimizes the squared sum of the residuals. So remember, the residuals are the vertical distances between each point and the line. And these distances can be negative and positive. Some points are above the line, some points are below the line. If you would sum them all, it would sum to 0. This is not helpful. But we take squares, negative values squared are positive, and positive values squared are positive. So then we get a large sum of positive values. And because it's squared, we weigh larger differences more heavily and smaller differences less heavily. So we can, for each point, we can calculate the vertical distance to the line, we can square it, we can then sum all those squared residuals, and that gives us one number, the residual sum of squares. And what ordinary least squares does is try to estimate beta 1 and 2 such that all these sums of squared residuals are the lowest possible. And so if you see a cloud of points and a relationship and you would draw a line, if you would guess the regression line, you tend to not exactly guess the OLS line. You tend, because your eye will look at perpendicular distances between the points and the line. But the regression only looks at the vertical distances. So it minimizes the vertical square distances between the line and each point. And OLS is very heavily used, primarily because it's what we call blue. Among the linear models, it is the most efficient and the least biased.